So first we had a long proof of the statement about what can be called homotopy lifting property of projection covering. So there was a map. We were given a map from let's say y times an interval, which to x, which can be understood as a homotopy of maps between pair of maps from y to x when we restricted to 0 or 1, and then we had a covering space x tilde. There was a projection to x, and so this was by f, and then there was a question about lifting this homotopy, the homotopy between between maps from y to x tilde, so that the lift would be such that this diagram would commute, and there was statement that such lift exists and unique once we fix the restriction of f tilde to 0. So exist and unique if you know informally, right? If you know f tilde, if you already know the restriction of this map 0, and then we can uniquely recover the whole map, the map on the whole interval. Okay, and there was two corollaries. First was a corollary which follows from the general statement when y is a point. So there was a lift of this was a statement that we can lift a path uniquely. So now y is a point, so this map comes this was a path, and we can uniquely lift a path to in x to a path in the covering space once we fix the initial point of the lift, and when y is itself an interval, we can use this general statement to lift a path homotopy. If you know a path, and again we fix the lift of the initial point of a path, and then the statement that, and we have some path homotopy in x, the statement that can uniquely lift a path homotopy between lifted paths in x tilde. And then we started to show the isomorphism between this fundamental group of S1 and the group of integers. Started the proof of the statement by 1 of S1. Isomorphic to Z. And so again, we just did it by explicitly constructing. We started doing this by explicitly constructing isomorphism. What we did is the idea was to construct again here S1 realize as R model integers, and in particular, so if we fix our base point to be a 0, the class of 0 here, so 0 modulo 1. We consider a map which we called alpha to Z, so that if we take an element in this group represented by some loop starting and ending at 0 mod 1, we send this to the value of the lift of this loop f at 1. So f tilde, this is just a reminder what we already did last time. So f tilde is a lift of f, which is a path in our circle with coinciding endpoints. So it's a loop representing some element here, and so f0, f of 0, f of 1 is equals 0, mod 1, and f tilde is a lift with respect to the covering map from R to S1, which is justified by this quotient. T goes to T1. Okay. And again, so we can keep in mind this kind of schematic picture that S1 is kind of some sort of we visualize it in some horizontal plane, and then R we can visualize as a spiral which projected to this circle in this horizontal plane and just orthogonal projection. Point 0 mod 1, so I keep mod 1 so to emphasize that this is a point on a circle, and this was, for example, 0 in R. We go, for example, if our path f goes once around the circle, and so we are lifting it to go to 1 here. So in this particular case, example, this f tilde of 1 is 1. So here we fix, in our definition, we fix a lift to the so that f tilde of 0 is 0 in R. We need to do this in order for lift to be unique. Okay, so again, this was a reminder what we already did last time. Are there any questions? So first, we want to show that this map is actually well defined, so it's independent of the choice of representative. So let's take another representative. So it's path homotopic to F. And suppose it's path homotopic with some homotopy F, but this means from one of the corollaries to which we just considered, there exist so if we consider lifts of f prime and f, and there exists a unique lifted path homotopy between them. First of all, we know that these are lifts such that, again, they're uniquely determined by the condition that at 0 they are fixed to be zeros, and then we have a lifted path homotopy between them. And but since they're path homotopic, it necessarily follows that their endpoints of this path, they should be the same, the lifted paths. Okay, and but then by definition of our alpha, if I use my representative f prime instead, the value of alpha is defined to be the value of its lift f tilde prime at 1, which we showed the same as f tilde of 1, which is the same as, again, by definition of alpha, as the value of alpha of the class represented by f. So indeed, it's independent of the choice of representative. So this we checked. And now we want to show, okay, so this is a well-defined map, but we want to show that it's actually group homomorphism. So we need to check that it respects the group operation here. So we want to take, so let's take, so we need to consider group operation on a pair of elements. So let's take another loop in S1, let's denote it by G. Again, it has a base point at 0, 1. And we know that, again, by the same, applying the same arguments, there exists a unique lift G tilde such that it starts at 0. So suppose I draw it here. Suppose G now will be a loop which, let's say, goes 2 times around the circle, but in other direction. And so if I want to lift it, so I start at this point, and then I go in opposite direction, and I go 2 times. So I will end up in this spiral. This infinite spiral, I end up kind of 2 floors down. I will end up at -2 in this example. Our example of the value of G tilde of 1. Yeah. The values of G tilde is the same as the value of F tilde at 0, which is 0. Okay, and now let's consider what we can do. We can consider a different lift. There exists also unique lift, but with a different initial condition. There exists a unique lift which we call, let's say, G tilde prime, such that it starts at well, it can only start at integer point because the projection of this should be still 0. The projection should be the same as G of 1, which is 0. So it only can start at integer point, and we can choose this integer point to be the same as the value of F tilde of 1. So we could instead, what we could do instead is we could start at this point, which is f tilde of 1. So we start at this point, and then we do the same thing. Start at a different point, and would end up here. So this would be erase this. So this would be g tilde prime of 1. This was g tilde of 1. Okay, and what we can also consider is the there exists, you can consider a lift of composition of f is g, and which starts again at 0. One can argue that this lift is given by the composition of can be chosen to be a composition of g tilde prime with f tilde. So this lift, which is lift of combination of G and F, can be chosen to be this. So we know that the lift, once we fix initial conditions, the lift should be unique, and this satisfies all properties needed for a lift, because we know that these we definitely know that this composition of this path of this path with projection gives us composition of f and g. And okay, first I mean, of course, this composition is well defined because the indeed the initial point of g tilde prime coincides with the terminal point of f tilde. So this is well defined. So this is a continuous path, and because if you compose it with a projection, you know that this is the same as a composition of paths obtained by composing projection with each of them. So this is a composition of functions, and this is a composition of paths. And since we know that this is lift of G and this is lift of F, this is F, G, indeed G composed F. So it's indeed a lift, and it satisfies satisfies the condition that it starts at 0 just because f tilde was chosen so that it starts with 0. So then we're ready to check what happens if you apply f. So if we apply alpha to a composition, to a product of classes corresponding to G and F. this give us some element in the fundamental group. So now we can, first we can use just the definition of the product in the fundamental group to argue that this is the same as alpha applied to a class of the composition of paths F and G. And then we apply the definition of alpha, which tells us that this should be a value of its lift starting a lift which is chosen, so the initial point is 0, and then we evaluate this lift at 1, but and so then this should be a terminal point of the second pass here, which is G tilde prime. And this is easy to see that this is should be the same as sum of G tilde of 1 plus F tilde of 1. So here G tilde of 1 is a value of a lift at 1, where lift is chosen so that it starts at 0. This can be argued because easy to see that for any s, for any argument s, G tilde prime of s should be equal to G of s plus F tilde of 1. So this is because, again, because of the uniqueness of the lift, the right-hand side provides us, G tilde. The right-hand side, of course, provides, again, the lift of G, because this is projected to 0, and this is projected, because since it's an integer, and this is projected to G of s. And it satisfies the required initial condition here, because G tilde of 0 is 0, so we have a correct initial condition. So this is indeed the case. And from the other point of view, again, using the definition of alpha, this is the same as alpha evaluated on a class of F plus alpha evaluated on a class of G. So we get that the alpha of the product of two elements of the group is indeed gives us well, the product in the group of integers, which is here, is a sum. So indeed, alpha is a homomorphism, so it respects the group law. Any questions? And again, from this example, this can be easily seen, so that yeah, the composition gives us -1, so it's a +1, which is the value for F, and -2, which is a value for G. So, and the sum is -1, which indeed where we end up by composing the lifts of these two paths. And another way to see that we kind of we essentially count the full number of rotations which we do when you go around the circle. So we went once in the counterclockwise direction and 2 times in clockwise direction. So in total, we went once clockwise direction. Okay. Okay, then, but we want to show that it's not just arbitrary homomorphism, we want to show that this is an isomorphism. And it's enough to show that it's bijective. So bijective homomorphism is necessarily isomorphism. So first, we will check that alpha is surjective. So that any integer can be obtained in this way. And to show that for any integer, there exists a loop on a circle which for which alpha gives us this integer, and we take f to be a loop in S1 defined by the following formula. So S here is taken to n times S mod 1. So this is a well-defined operation, mod 1. For when S is 0 and 1, you get the same. So this is a continuous function because when S is 0 and 1, this is the same modulo 1. And so what about, so to calculate the value of alpha, by definition, we need to find the lift of f, and lift can be chosen to be a map which sends S to, well, essentially the same expression. By that, now it's given by the same expression, but now we don't consider it's modulo 1, it's just a value in R. And it satisfies, again, the required property that it starts at 0. So it's indeed the lift which we should use. And then if you calculate the value of alpha on a class of f, by definition, this should be f of 1, which is n. And again, geometrically, this is just a path which winds n times around the circle. Okay, and next, we'll show that this is injective. Suppose we have a pair of classes represented by loops f and g, for which the value of alpha is the same. And then we have to show that these classes are actually the same, so we need to show that f and g are path homotopic. Okay, so by definition of alpha, this means that the lifts, as we had before, should have the same value at 1 at the terminal point. And but then it follows there exists a path homotopy was known by f between lifts tilde, which can be given by explicit expression, just a linear, essentially linear homotopy connecting these two paths. So this is considered an element in R. So we can, so G tilde of S. So we can add them up and multiply by real numbers. sorry. Well, actually, we don't need. We need path. We need actually path. Sorry, we need path homotopy between f and g themselves. So we want to consider this model 1. So this is an element in R. Shows that f and g are path homotopic, and we do this by giving an explicit path homotopy between them, but in this path homotopy we are using their lifts f tilde and g tilde. So this gives a value in R, but then we take it modulo 1, and this gives us in R mod z, which is our S1. And it's, of course, a continuous function, which because it's just composition of continuous functions, and f obviously f as 0, for example, is equal to f tilde of s mod 1, which is we know the same as of s by definition of the lift, and similarly f of s comma 1 is tilde of s 1, which is the same as g of s. So indeed, this is f is a path homotopy between f of s and g of s. Well, okay, in principle, we also need to check that these the boundary conditions are satisfied. So f of 0 t, for example, is equal to t times f of 0 plus 1 minus t g0 g tilde of 0, but this is just 0, and also f of 1t is equal to t f tilde of 1 plus 1 minus t 1. But these are the same, so this is just f tilde of 1, because they're the same. The result is independent on t as we want, so it's indeed a path homotopy. Okay, so we check that these f and g are path homotopic, so these classes are the same. So we check this is injective, and then it follows, finally it follows that. So combining the fact that alpha is a homomorphism, it's surjective and injective, we conclude that alpha is an isomorphism. Indeed, this is these two groups are isomorphic. In particular, we also know how to what is a kind of generator, how to get a generator here. So the generator is just given by this, for example, represented by a loop f with n equals 1. It's just a loop which goes once around the circle. Concludes the proof. Are there any questions? If there are no questions, let me mention some immediate applications of this statement about isomorphism between the fundamental group and the group of integers. First statement is known as Brouwer fixed point theorem. Okay, of course, what we are going to consider here is not an original proof by Brouwer. The statement is the following. So consider H to be a continuous map from a disk to itself. Consider this disk to be a closed disk, so it includes a boundary circle. Then the statement there always exists a point on this disk such that the value of h of x is the same as x. Of a two-dimensional disk, and we consider a continuous map from it to itself, and the statement there always will be some point, so it's preserved by this map. Quite a interesting statement, simply formulated. And can be, well, in principle it's not real to show, but if you already know this result, the machinery of the fundamental group, and we know the fundamental group of the circle, the proof becomes quite elementary. So let's prove it by contradiction. So suppose this is false, and h of x is not equal to x for any x in the disk. And then we can use this fact to define a map, let's denote it by R, from a disk to a boundary circle. And so geometrically, this map is defined as follows. So let's suppose we have some point x, arbitrary point x here, and we want to define its value R, which will be some point on the boundary circle. And what we do for this, let's consider the value of h of x in this disk, which must, by our assumptions, this should be two different points, right? If not, for all x's. If not, we come to contradiction. And then what we do, we draw an array starting from h of x and passing through x, and we look where it intersects the boundary of the disk. As usual, I remind you, the disk here we understand as a subspace of elements of the norm not greater than 1 in R2. And this will be, this point of the boundary will be our value of R of x by definition. And since h of x, this h of x is continuous, it will follow that R of x is continuous. And we also know that, okay, so what happens when x, if x itself is, if x is already on the boundary, then by definition, r of x should coincide with itself, right? Because the ray is already intersects at this point. So r of x is equal to x if x belongs to this boundary circle. Basis. Means that R, if we restrict R on this boundary, it's just identity. This means that by definition, R is a retract, is a retraction. This boundary is a retract. Okay, and now what we want to do, we want to take any loop in this boundary circle. This is some f here on the boundary, and of course this can be also understood since this circle is understood as a subspace in the disk. This also gives us a loop in the whole disk. And so let's say initial points, initial and terminal point is some x0. The boundary, let's say x0 here. And we know that it's contractible. Contractible as a loop in this disk. Why is that? Well, again, we can just use a linear homotopy, as we already used at some point by considering maps inside the disk. So let me explicitly write this. Path homotopy is a function of S and T, which is by the following expression. F when meaning, okay, this meaning the restriction for T. So F, when T is restricted to 0 is equal to F, and F is, when T is restricted to 1, gives us a constant loop at x0. So you can just follow that any loop here can be contracted to a constant loop in x0. And but then it follows that it is also contractible in S1, as a loop in S1, by path homotopy, which is composition of this homotopy F and R. This is because we define this continuous map R from a disk to the boundary circle, and we know that R on S1 is identity. Particular, if we restrict this composition to t equals 0, well, f restricted to t equals 0 gives me f, but f belongs to the boundary on which R acts as identity, so it's still f. Well, now consider it as a path in S1. And if we restrict this composition to t equals 1, again, the f here is valid also in the boundary, and R is identity on the boundary, so this is also just the same. 0. The difference here is these are understood as a path in the disk, and these are understood as a path in its subspace, in this boundary subspace. But then it means, then it would imply, so for any, so we started with any loop on a circle, and we showed that it's actually contractible. So it's path homotopic to a constant loop. This would imply that f, the class of f is 0 in the fundamental group of a circle. But we know that this group is not trivial. And f was an arbitrary loop. So we come to a contradiction. This gives us a proof of the theorem. Any question? Second application which I want to mention is what is called Borsuk-Ulam theorem. And the statement is the following. It's kind of a bit similar to the previous statement, but not entirely. So the same is the following. So for any continuous map, a continuous function f from S2, a two-dimensional sphere to R2, two-dimensional Euclidean space, there exists a unique, sorry, not unique, just exists X on the sphere. Well, here we understand the sphere as a subspace in R3. So as usual, visualize something like this. It's a subspace of elements with norm 1 in R3. And the statement that there exists a point x here. So we have a function from S2 to R2. And we want to show that there also exists a point such that f of x is equal to f of minus x. Minus x here meaning minus is an operation in R3, so minus is an antipodal point on S2. So for example, if x is a north pole, minus x is a south pole. So we want to show that there exists a point such that the value on it of the function is the same as the value of the function on the antipodal point. Okay. Again, we will show it by contradiction. So assume that this is not true. Point x to sphere, and then we can again use it to define a certain map. It can be mapped from S2 again, valued in a circle. Here, circle we understand not as R mod Z, but let us understand circle as a subspace, as usual subspace in R2. Of the elements on 1 circle, and point on S2 will be mapped to the following, up to f of x minus f of minus x divided by the same thing, the norm of the same thing. So this is again. So this is element in R2, which is understood as a vector space. So we can consider minus the differences here, and then if you divide by norms of this element, we by definition we get an element of a unit norm. So it indeed belongs to subspace S1, and this is well defined. There is no issue in the denominator, so it never vanishes because of our assumption. And it's a continuous function because it's a composition of continuous functions. And we also want to define the following auxiliary map. Eta will be, well, actually, this will be just a loop. As in our S2, again, this is a space in R3, which is can be drawn like this, and loop S, an argument is sent to following point. Sine 2 pi s. Well, I'm just write the coordinates in R3. Sine 2 pi s, and the last coordinate is 0. So it's definitely, it belongs to this sphere, but moreover, it actually belongs to, so since the z coordinate is 0, it actually belongs to the equator. So you can send eta as a loop, goes once around the equator. Okay, good. And then, okay, so we define G a map from S2 to S1, and then we define a map from from an interval to S2 here, right? And then we can consider composition shown by H is a composition of eta G. This would be a map from an interval to 1. And okay, we just do the composition of these two maps. And we can notice the following, that that it satisfies the following property, that H of well, let me, it satisfies the following properties, is that H of S is equal to minus H of S plus half. So let us show it. Let us show this. Why is this the case? Okay, so first we note that eta of S plus 1/2 is equal to minus eta of S, right? So eta is just, well, you can do this by just using explicit expression, but you can also notice that, well, eta goes once around this loop, so around this equator. So if you consider some point S here, value of eta of S here, S plus 1/2 will be a value which you get by going half of the equator, and this will be go half around the equator. This will be it will have opposite value, and then you also use a property that G of minus X is equal to minus of X. And this is just follows from this expression. So if you place X to minus X here, this expression will change the sign. So from this follows that the H, which is a composition of these two maps, satisfies this. So again, here H is considered as valid in a circle, which is a subspace in R2. Okay. Okay, so we have this H. Okay, let me write it. So H was a loop. One. Here, it's a bit different from what you had before, in the sense that S1 here is understood not as R mod Z, but understood as just unit circle in R2. This, but still, topologically, it's the same space. So this is still, of course, isomorphic to homomorphic to R mod Z, which we considered before. And at some point I explicitly wrote how you construct this isomorphism. And so they exist, you can still consider consider lift of this map, unique lift H tilde should be a pass in R. And here we consider a lift with respect to projection R to S1, which in this representation of S1, this sends T to cosine 2 pi T comma sine. Unique lift such that it starts at do I need to worry about where it starts? Maybe I don't. Yeah, I don't need to worry where it starts. So let me, just exist some lift. If I don't fix where it starts, we still know this exists. First, I fix where it starts. It will be unique, but this is not going to be important for us. So we just consider some lift, and so we know that the path H itself satisfies this condition that H of S plus 1/2 is equal to minus H of S, right? And it follows that so the lift is should satisfy the following condition says that H tilde of S should be equal to H tilde of S plus 1 S plus 1/2 is equal to H tilde S plus M plus 1/2, where M is some integer. It's because if you have so H tilde for a fixed argument, H tilde is a certain preimage of H tilde of S is a certain preimage of H of S under this projection. So if you had two elements in S1 which differ by signs, this means that the corresponding value of T they differ by an integer plus 1/2, right? If you shift, well, this should be obvious, right? Because if you, of course, the addition of integer doesn't change anything, but if these two vectors in 2 dimensions they differ by sign, then the corresponding arguments they should the corresponding value of T they should differ by 1/2 plus an integer. Well, okay, if you wish, maybe what I said was a bit confusing. What I just mean is the following. So if this is have something for 2 values of T, you have here we have T1, and here we have minus same thing, but instead we take T2, then it's this equality is equivalent statement that T1 is equal to T2 plus m plus 1/2, where m is some integer. Right? Different only. So since h is a value of projection of h tilde, this equality becomes this equality for the values of h tilde, at least for any s. And we also know that well, so h is continuous function. So this is, in principle, you could imagine, okay, m depends on s, but this actually couldn't happen because m is an integer, and this is continuous function of s, and this is continuous function of s, and an integer value function which is continuous is always a constant. So m is independent of s. This is so we have the same m for any value of s. And then we can use it as follows. So let us write, let's use this equality when s equals 1/2. It will look like this. So h tilde of 1 is equal to h tilde of 1/2 plus m plus 1/2. And then we will use it once again by using this equality when s equals 0. And this will give us h tilde of 0 plus 2m plus 1. And so okay, good. So if yes. So let's, what next we should say is that this h, h represents a certain element phi 1 of S1 with a base point where we start our loop h, which is the same as h of 1. And we can repeat the same argument as we had for when we showed that the proof that this is isomorphic to the group of integers. So consider similar map alpha, possibly for a different choice of base point here, and we would then have that the value of alpha, which construct is the same, just which instead of 0 we have some h of 0, we would have that the value will be corresponding to the difference between the value of the lift at 1 and the value of the lift at 0. So this will be h tilde of 1 minus h tilde of 0. And so before we just chose this in our proof we chose it to be 0, but in general you just have to subtract this, and this is, we show that this is equal to 2m plus 1, and this is never 0, right, for any m, because this is an odd integer. For any m, it's never 0, and this means that H is not contractible. Okay? The not contractible loop in S1. But from the other point of view, well, let me, this part. From our point of view, we can notice that eta was a loop in S2, which is just the equator, is contractible. So as a loop, in principle, one can present the explicit path homotopy, but to doing this, but it's obvious. You just kind of what we can do is just kind of slice this. For example, take a plane and start rotating this plane, so this loop just contracts to a constant point. And I mean, at any given. So we consider whereas a plane slices this S2, and we start rotating it until it just touches this S2 at one point. And this will give us a continuous map which takes this equator to just a to just a point. And but then H was given as a composition of with some path. So if we can contract eta, if we can homotop eta to a constant map, then we can homotop this composition to a constant map. Is path homotopic constant. And this was our H by definition. This is, again, we arrive to a contradiction. Since we argued that H it should be a non-trivial element. Any questions about this proof? Okay. Yes, this was an example of application of this statement about pi 1 of the circle. Well, next will be a proposition which helpful for calculation of fundamental groups of other topological spaces, and is the following. So assume we have a pair of pi path-connected topological spaces. So again, we shouldn't worry about the choice of base point when we consider the fundamental group. And then we want to make a statement that the fundamental group of a product, this is a topological space with a product topology, is isomorphic to a product of the fundamental groups. Again, since the path connected, we shouldn't worry about up to isomorphism. We can forget about the base point, and the product is also path connected, and we also can forget about base point here. Well, this follows more or less from the definition of the product topology, but okay, let me write it more explicitly. How do we prove this? So for any, by definition of the product topology, if you consider a function from a topological space Z to the product x and y, and so suppose this function, this value of this function, some element Z, here is given by the pair of values, say f of z and g of z. Oh, sorry, it's a bad choice of notation. H of z and g of z, where so one can make this following statement that where h is a function from z to x, and g is a function from z to y, then this f is continuous, the function from z to a product, if and only if h and g are continuous. Okay, so yeah, we'll use this statement from the general topology, which you should add when you consider the product topology. In particular, one can use this statement and take z to be an interval, and then so f, if you take f loop in product, so that initial and terminal point is given by pair x0, y0, so x0 is some point in x, and y0 is some base point in y. This means that so that again, suppose this S explicitly it has components H of S and G of S. The statement that F is a loop is equivalent to the statement that H and G are loops X and Y are respectively based at x0 and y0 respectively. This one correspondence between loops in a product and pairs of loops in individual spaces. And if you take a Z to be now a product of two intervals, this means that you consider maps from a product of two intervals to x and y, which correspond to some path homotopy. This general statement for general Z then tells us that a path homotopy x times y, the pair of path homotopies x and y separately. It means that in particular in the notations of this previous observation, where we have f a loop in the product, which can be so the pair of loops h and g in the individual spaces. This means that we have some f prime, which is path homotopic to f, and with some, and suppose this is given by a pair of g and h. As before, this is given by the pair of h and g, and this is given by some new pair h prime and g prime. It will follow this statement that f prime is homotopic to f is equivalent to the statement that individually h prime is path homotopic to h and g prime is path homotopic to g. And this means that there is a bijection. So there is one-to-one correspondence between equivalence classes of the loops in the product and the pairs of equivalence classes in the individual spaces. The bijection between pi1 like 0 times pi1 y is base point y, and the pi1 of the product is base point there is this equivalence from the just for the loops, because a loop in a product is a loop in a product is equivalent is the same as a pair of loops in x and y, and this equivalence relation, the path homotopy equivalence relation respects this. Class of h, class of g corresponds to a class of map, class of the loop given specified by a pair of h and g. And moreover, it is a homomorphism. Why is it homomorphism? Well, it's kind of tautological, but okay, let me write this. So this is, we consider the composition of pairs here in the product of fundamental groups. So consider in the product of group, see the pair of classes represented by H1 and G1, and we want to compose it with a pair of classes represented by H2, G2. So by the definition of the product of the group operation in the product of groups, we will just do the individual operations for each component. So here we're just using the definition of the product of groups, and now we use a definition of the group law in the fundamental groups of this individual x and y. So this is the same as the composition of class of the composition of H1 and H2, and this is the same as the class of the composition of G1 and G2. But this is under this bijection corresponds to a class of the loop given by the pair of loops H2 composed with H1 and G1 composed with G2. But since when we compose loops in the product of spaces, this is the same as taking this composition of loops specified by the corresponding pairs. And then we use the definition of the product in the fundamental group here, fundamental group of a product. The product of classes corresponding to this pair and the class corresponding to the other pair. So we show that this bijection respects the group loop. So this means that we have an isomorphism. Any questions? So this is any questions? So this is where we stop this lecture. If you have some questions, let me know.
Excuse me. Yes. Hello.
Yes.
What will you be doing in the next lecture?
Well, the next lecture will be push forward the properties of push forward.
Okay, thank you.
Any other question? Well, if not, that's it for today.
Thank you.